Hello everyone. Welcome back to AP Calculus. So today I'm going to record both lesson and start the homework because we're going to do part B here, and I think it can be done in a portion of a week, and then I will give you a recording of the next lesson on top of this. Either that or it'll be paired with the last lesson, one or the other. Today we're going to talk about lesson 6.4, part B, which is called volume of rotational solids. So basically, up until now we've been using calculus to find the area under curves. Today we're going to take that one step further, and we're going to talk about how to use integrals to find volume of a solid. Now, depending on the shape of the solid, the equation could be tricky to figure out. But once you figure out what the actual equation of the sides of the solid look like, then then you can move forward fairly simply. So I want to make a quick example here of what I'm talking about. So let's say that I wanted to make this solid figure. I have some sort of wheel that spins around on an axis, and maybe it has a roller on top of it or something. It's some sort of conveyor belt wheel or something like that. And I want to find the volume of this figure. Well, the volume of this figure would be really difficult to find because it's not a cylinder, and it's not a cone. It has this odd curved shape to the side. Well, if I can pinpoint what this odd curved shape could look like as a formula, then I could move forward in trying to find the volume of this actual figure. So the next thing I did was I tried to piece that together. So I found a formula that gave me a curved shape. So I know that a curved side like that is parabolic. So I'm talking about some sort of parabola that I'm dealing with. So I created a parabola out of my shape. And then on top of that, I needed to stretch my parabola out. So it wasn't tall and thin, but it was short and wide. So I made my A value of my parabola 1/8. I knew I wanted my parabola to smile so that it'll give me a full rotational solid. And then I knew I needed to start it above the axis because I need this width. And whatever this width might be, whatever that might be, that's the distance up I needed to travel up the axes. So in my case, I moved it up 4 units, but that isn't necessarily what all of them will be. Now, your job today won't be to create any of these formulas. You're not going to be trying to figure out how to make a rotational solid using a formula. They're going to give you a formula, and you're just going to have to figure out what the volume is. So you don't have to worry about that process, but I wanted to give you an idea of my thinking because I completely made up this example. I didn't just pull it out of the book. I do have one coming out of the book, but I wanted you to be able to see where my mindset came from when I went to create this particular example. So now I need to cut the ends of the figure so that I have a starting point and an ending point to give myself my designated shape. So now I have basically my designated shape of my roller here. Now you'll see that this is sideways compared to what the roller is. And it doesn't really matter. I could have made it up and down. The trouble with making something like this up and down is now I have a sideways parabola, and so now it's no longer a function. So I would have had to deal with some dy dx's. It's much easier to make them rotate over the x-axis then rotate over the y-axis. And then I'm going to take this thing and I'm going to spin it around the x-axis to create my figure. So if you take it and you rotate it out and around in 3 dimensions, all the way around, all of a sudden, I have a shape that looks extremely similar to this. Now we need to talk about how to find the volume of this, because I've created the formula and I know how to make it by spinning it around the axes, but I need to figure out how to create a formula that actually finds the volume of this thing. So if you remember back to the first part of this lesson, we talked about cutting these regions into little rectangles using Riemann sums. So I'm going to cut each region into a rectangle. But now, when I go to do that, what happens is my little rectangles, and actually Riemann sum works really, really well on something like this because I basically lose as much area on this side as I gain on that side. It's really close anyway. But what happens is I end up spinning these rectangles. So I no longer have rectangles, I actually have these odd little discs. So I have a disc, a solid disc of rotation like this. So, and they're 3-dimensional, so it's like, they're like a circular disc. See if I could make it look like that. I can't really, I'm doing a terrible job. So I have a circular disc like this, and this is just a chunk of this. So this solid figure is now split into all of these little discs that could be stacked on top of each other. Think about like that Goofy Kids game where you've got the big peg in the middle, and the kids have to put the biggest ring on the bottom. So I've got my big ring, and then my smaller ring, and then a smaller ring yet, and then a smaller ring yet. And they have to stack them on the peg in the right order. So what we're doing is we're taking this figure and we're cutting it into discs, into rings. And we're stacking them on top of each other to get the volume. Now, just like in the last lesson, we're going to take the width of those discs, which is currently 1, and shrink them down. And shrink them down, and shrink them down, and shrink them down until they're so minuscule that each disc is just a little slice, like a CD, stacked on top of each other. So I have like tons of little CDs that are all different widths that stack on top of each other to make this nice solid figure. And then I need to go ahead and use calculus, use an integral, to pull all of those CDs together. Now, over here, we're talking a little bit about volume because we've moved from area to volume. In our last example, we were doing area, which was just length times height, right? It was base times height, base times height, base times height, and we shrunk the base down, so the height became the only thing we cared about. The height gave us everything, the actual base gave us nothing, so we just took the integral of the function, which was our height, over the region that we wanted, and that gave us our area. This time it's not quite so simple. We need to deal with the fact that we're working with volume. The volume formula is pi r squared h. That's the volume of a circular disk. So pi r squared is the volume of a circle. So if I have my circle, the area of this circle is pi r squared, and then I switch it to a disk, now I have this height that I have to account for. Yeah, it was a terrible circle, but now I have this height I have to account for, so it ends up being pi r squared for the circle times the height, which is also the volume formula for a cylinder, because basically these little discs are tiny cylinders. They just don't have much height, but they're basically cylinders with very little height. They are cylinders with very little height. So now this becomes the formula that I need to integrate. In my example, I went from -4 to 4 across my figure. So I'm going to take the integral from -4 to 4 of this pi r squared h. Pi is just a constant, so the book will often move it to the front so that we don't have to deal with its actual integration. Now r is the interesting piece here. The radius of these discs is the distance from the center of the disc out to the edge. Well, that's the answer to the formula. So this is r. Whatever the formula is, that's going in for your r value, because the r value is the distance from the center of our figure out to the edge, wherever that edge may be. And the edge is a changing value based on this formula. So r becomes our formula. And then h. H is the height of each cylinder. Currently my h values are all 1, but like I said, I'm going to shrink them, and then I'm going to shrink them again, and then I'm going to shrink them again. And what h becomes is it becomes this tiny little difference, this delta x amount, that's going to be so minuscule that it basically disappears from the formula completely. Just like on our formulas yesterday, when we were doing our Riemann sums, we did base times height to get the area of each rectangle. However, the base shrunk away and we just used integrals on the height, which was the formula. So you just do the integral of the formula. In this case, we don't quite have just the integral of the formula. What we end up with is pi times the integral of the formula squared. Now my formula in this case is 1/8 x squared plus 4, and I want to do that all squared. So I take the integral of my formula squared, and then I'm going to multiply the answer by pi. This is one of those instances where if you want to multiply in the pi when you're done, you're welcome to. It's not necessary. You're going to get crappy fractions for a lot of these. And I made up this problem, so it's probably going to be particularly bad fractions, but we'll see when we get through it. All right, now we need to solve this. The first thing we want to do is FOIL out this inside, which, because of the problem I picked, is a little trickier than some of them in the book. So I rewrite it, 1/8 x squared plus 4. Okay, so I'm going to have 1/8 x squared times 1/8 x squared, which is 1/64 x to the 4th. And then I have 1/8 x squared times 4, which would be 1/2 x squared. And I have 1/8 x squared times 4, which would be 1/2 x squared. And then I have 4 times 4, which would be 16. So when I clean this up, it becomes pi times the integral of, from -4 to 4, 1/64 x to the 4th plus 1/2 x squared plus 1/2 x squared would be 1x squared. That actually turned out pretty nice. Plus 16. It's just this one that's going to be particularly gross. Alright, now we're going to go through and take our integral. So that becomes the region between -4 and 4 of 64 times 5. 1/320th x to the 5th plus 1/3 x to the 3rd plus 16x. This one's going to be the big factor down here. He's going to make the most noise. So I have 1/320th times 4 to the 5th plus 1/3 times 4 to the 3rd plus 16 times 4. That is 1,328/15, or 88 8/15. Minus. Same deal with -4. Slightly different though. And then we still have this pi out here. Don't forget about him. Okay, so I have 1/320th times -4 to the 5th plus 1/3 times -4 to the -4 to the 3rd plus 16 times -4. Okay, which is the exact same thing, only negative. Good. That's what I figured it would be. 13/28/15. This chops. So I have 13/28/15. And 13/28/15, which is 26/56/15 times pi. This is totally an acceptable answer right now, but if I multiply the pi, my area is my volume is approximately 556.27 units cubed. Now, hopefully that makes sense to you. The biggest thing is being able to work it from here on down. The explanation was minor in comparison. All right, I'm going to do one example, and then I'm going to do a homework problem. And the homework problem I'm going to do looks scary, but it's actually one of the easier ones. But I was afraid because it looks scary, you might shy away from it. And then I'm going to give you the homework assignment to work on for a while. So it's not a very long assignment. Hopefully it'll go fine. And just like always, I'll be available for help over all the regular pathways. Example 4-5. Y equals x squared plus 1 from 0 to 2 as a solid of revolution. All right, so on this one, we can just dive straight in. We don't have to play around with the picture or the shape or anything like that. Okay, so immediately our formula is pi times the integral of our region, 0 to 2. This is going to be a little bonus. Of this squared, x squared plus 1 squared. Now, like I said, the book picked a much nicer one. It was because they weren't trying to get a very great picture. They didn't care about what the picture looked like. They cared more about making it easier to work with than making it look exactly the way they wanted to. Whereas I cared more about the way it looked so that I could really demonstrate how this works. Now, we square this out, FOIL. That gives us pi times the integral from 0 to 2 of x to the 4th plus 2x squared plus 1. We write it twice. We have x squared plus 1, x squared plus 1. So our first give us x to the fourth, our outers give us 1x squared. My inners give me 1x squared, which makes 2x squared, and my last give me 1. Now I want to go through and take the integral of this. So that becomes the region bounded by 0 and 2 of 1/5 x to the 5th plus 2/3 x to the 3rd plus x. I'm going to give you just a second to make sure that everybody is solidly within that. All right, now we're going from 0 to 2, so 0 is just 0, so I just need to put in 2. So I've got 2, 4, 8, 16, 32, so this will be 32 fifths. In the middle here, I have 248 times 2 is 16 thirds. And then out on the end, I have plus 2. And I'm going to times that all by pi. So I'm just making sure that I'm getting everything right. I don't want to do anything incorrect while I'm working with you here. So what we end up with is 13 and 11/15, or that's 206/15 times pi. So your answer could be 206/15 pi, 13 and 11/15 pi, or if you multiply in the pi, if you take either of these numbers times pi, in the end you end up with 43.14 units cubed for our rotational solid. Hopefully that went okay. That's pretty typical of most of the problems you're going to deal with here. There are some that are just a hair trickier, but for the most part, I think they'll go really fast and fairly simple for you. And the last lesson should go really smooth as well. It just is a little more time consuming. All right, now I'm on page 409. I'm going to work on a homework problem. Your homework tonight is going to be 18 through 23 tonight. Your homework over the next whatever days is going to be 18 through 23. But I'm going to do problem 22 with you. So problem 22 gives us the function y equals the square root of 4 minus x squared, as our function that we need to rotate, and our region goes from -2 to 2. So we're going to use the same formula system. This looks nasty. It looks like we have a chain rule situation here. It isn't though. It's going to actually fold out really nicely for us. There are actually worse problems hiding in what we're doing, and a lot of them that you have to foil, like the early ones, are actually worse off than this one, because this one is actually going to kick itself away pretty nicely. Anyway, let's dive into it. We want to take the integral from -2 to 2 with pi out front of the square root of 4 minus x squared all squared. Now what you'll notice almost right away, hopefully everyone notices, that this square root and that square will just cancel each other. because they're just opposite operations. So the square root and the square knock each other out. So I end up with the integral from -2 to 2 of 4 minus x squared, because the square root and the square have just dissipated. Now when I take that integral, that becomes pi times the region from -2 to 2 of 4x minus 1/3 x to the third. Now I can go ahead and plug things in. So I'm going to end up with pi times 4 times 2 is 8 minus 2 cubed is 8, so this becomes 8/3. So I have 8 minus 8/3, which is 2 and 2/3. So I have 8 minus 2 and 2/3, which becomes 16/3, by the way. Then, when I put -2 in, I have 4 times -2, which is -8. And then I have -2 cubed, which is also -8. I put that on top, so it becomes plus, because it's a negative, 8/3. Now -8 plus 8/3 is also 16/3, only it's negative. -16/3. This works out really nicely that way, because this region must have an exact mirror on both sides of the axes when I rotate it. And I think what I have actually is some sort of function that looks like this. So when I spin it, I'm actually spinning it around this axis and ending up with something like that, is what I would guess I'm ending up with. It might be a parabola, so it might even be, and it would only be half of one though, because of that. But you'd have to look at it to actually physically see what's going on. In the middle we chop chop, boom, boom. So I end up with pi times 32/3, which, if you want to multiply that out, 32/3 times pi is 33.51 units cubed. Hopefully all of those problems went well, and hopefully the homework will go well on 18 through 23. Again, I'm available during the time slots that we have, but I'm also available outside of the time slots we have. So if you guys really want to get together and have some sort of homework session outside of that time slot, whether it be over Zoom or on our Google Doc, or just emailing me back and forth, or whatever. I mean, just let me know so that I can help you out.